play an important part in the study of radar indicators, and by now you should be able to recognize a pip when you see one. Some are tall, some are short, some are friendly, and some indicate danger ahead. That's the way it is in radar, too. Pips indicate all kinds of things. An enemy task force maneuvering through fog or darkness, our own reconnaissance planes, the splash from a coast artillery shell, the answer to an IFF challenge, or perhaps this is the signal returned from an enemy rocket ship or guided missile. The electronic eye of radar detects and locates these targets. But for this information to be of any value to you, we need different types of oscilloscopes to present this data visually, accurately, and effectively. Some scopes measure range only. Others measure either azimuth or elevation. Some present data on both range and azimuth at the same time. And still others measure both azimuth and elevation. Now you'll see how these scope presentations are formed and how the scopes display the data they obtain. In the first film of this series, we reduced all radar sets into this simplified block diagram. You saw how the timer generates a voltage pulse and sends it along to the transmitter. At the same time, it sends part of each pulse to the indicator, where it starts forming a baseline. Back at the transmitter, the pulse is converted into high-frequency energy, sent to the transmitting antenna and launched into space. However, a spillover of this energy escapes into the receiving antenna and goes down to the indicator, where it appears on the baseline as the main bang. The sweep of the baseline is synchronized with the outgoing pulse, so it can measure the time it takes a pulse to leave the transmitter, reach a target, and its echo return. When the outgoing pulse strikes a target and part of the energy is reflected back to the radar set as an echo, the receiving antenna's job is to pick up the returning echo and shoot it along to the sensitive receiver. Here, the weak echo is amplified and sent as a voltage pulse to the indicator, so it can appear as a target pip. Basically, that's how all radars work. And in the first two pictures of this series, you saw in detail how the timer, transmitter, and receiver did their jobs. In this film, we'll see how the indicator functions. Let's take a look behind the panel and see how this typical A presentation is formed. This scope picture, as well as all others, are created by a special type of vacuum tube called a cathode ray tube. There are two basic types of cathode ray tubes, the electrostatic and the electromagnetic. These tubes produce all the scope pictures in radar. Let's see how they operate. First, to review what we know of the electrostatic tube. At the rear end of the tube is an electron gun, composed of a heater, cathode, grid, and focusing anodes. The cathode, when heated, gives off electrons, which are formed into a stream by the grid. The anodes accelerate the electrons and focus them into a beam. The beam bombards the fluorescent coating on the face of the tube and causes it to glow with a bright spot of light. These plates deflect the beam horizontally. When positive and negative voltage is applied alternately to the plates in the form of a sine wave, the beam is swung back and forth like this. But when sawtooth voltage is applied, it causes the beam to sweep across and snap back quickly. At normal speed, we get this picture, or an apparent baseline. The pips are formed by the action of the vertical deflecting plates, which bend the beam up and down each time a signal pulse is received. Thus, you can see that the electron beam is affected by both the horizontal and vertical deflecting plates. This is the usual type of A-scope. But these two sets of plates, by working together, can form any number of different scope pictures. For example, by changing the polarity of the voltage on the vertical plates, you end up with an A-scope on which the pips appear as negative deflections, like this SCR 582. These scopes, on which the target appears as a single pip, are okay for early warning and range data, but they were not designed to give elevation and azimuth data. This is why. A pulse traveling through space follows a path closely resembling that of a searchlight beam, and the greatest intensity of the beam lies in a direct line through the center. The strength of the beam diminishes gradually to either side of center until it reaches a point of minimum strength at the edges. The pattern is called a lobe, which is nothing more than an imaginary plot drawn to indicate the intensity variations of the radar beam. Let's say we have a target in the center of the beam, where the intensity is greatest. The target will reflect a strong echo, and you'll get a good-sized pip on the scope. But if the target moves ahead of the beam to a point where the intensity is weaker, the echo will also be weaker, resulting in a pip that's barely visible. As you traverse the antenna to catch up with the target, the plane is in a stronger part of the beam, and you get a stronger pip. It's the same on the other side of the beam. Minimum intensity, small pip. Maximum intensity, full pip, always letting you know when your beam is pointed directly at the target. But here's why a single pip can't provide accurate azimuth or elevation data. When the target signal on your scope fades, did the plane move ahead of the beam, behind it, above it, below it, or is the signal just fading due to a faulty set? You have no way of knowing. And if you assume the plane's getting away from you and begin searching for it, there's a 50-50 chance you'll traverse in the wrong direction and lose the target completely. To remedy the weakness of the single lobing system, we switch this single lobe back and forth so fast that you have virtually two identical lobes. When you have a target, these lobes are represented on the scope by two separate pips, one for the right lobe and one for the left. When the target is centered between the two lobes, the pips balance. That is, they're the same height. But if the target gets off-center, naturally it's going to be in a stronger part of one lobe and a weaker part of the other. Here, for instance, the target's moved to the left, so the left pip gets bigger, the right one smaller. If the target moves to the right pip gets larger. To center the target, all you have to do is traverse the antenna toward the larger pip until the two pips are again balanced. Then you know the target is centered in your beam and you're exactly on target. Keep the pips balanced and you'll stay on target. There may be times when the pips will fade because of atmospheric conditions or a maneuvering target. But although they may become smaller, as long as you keep them balanced, your beam will still be on target. In order to project this split picture on the scope, the antenna, receiver, and indicator circuits must be modified. Let's look at the antenna first. The antenna is designed so it can receive echoes alternately, first from the right lobe, then from the left. Notice, however, that each lobe is on long enough for a pulse to be sent out and its echo to return from maximum range before the next pulse is sent out through the other lobe. To handle the echoes from each lobe efficiently, to keep them from being mixed up, a special receiver circuit is used which acts like a gate. This gate allows signals from the left lobe to pass through, and then those from the right lobe. The signals go down through the receiver alternately and onto the indicator. Hold it. That's right. Before they appear on the scope, the indicator must also be prepared to receive two echo signals and display them separately. Here's how the indicator works. When a pulse was sent out through the left lobe, at the same time part of that energy was sent over to the scope where it began forming the baseline. Thus, when the echo from the left lobe returns, it forms the pip on that baseline. When the lobe was switched and the pulse went out through the right side, part of that energy was sent over to the indicator also and began forming another baseline, so that when the echo from that pulse returned, it formed a pip on its own baseline. So that now you have the set sending out a pulse through one lobe, waiting for an echo, then switching to the other side, sending out another pulse, and again waiting for an echo to return before switching back again. Furthermore, the echo from each lobe appears on its own baseline. Normally, the two baselines are superimposed and appear like this. But there are still two separate baselines and two pips. On the actual scope, you may see them like this, and by adjusting your spread control, you can govern the distance between them. Okay, so now you know that by switching a single lobe back and forth often enough, we can get the effect of two lobes and thus stay on target much more accurately. So far, we've only been talking about the lobes that cover the horizontal plane and measure the azimuth of a target. But when you go looking for aircraft, you need elevation data too. So for those sets, we add another lobe, a vertical one this time, to flip back and forth and supply the angular height or elevation of a target, in the same way the horizontal lobe takes care of the azimuth. Of course, the same idea holds true. Each lobe has its own pip and baseline. When the target's centered in the lobes, the pips on the elevation scope are balanced and your angular height data is correct. If the plane gains altitude, naturally it'll be in a stronger part of the upper lobe, a weaker part of the lower one. So one pip grows, the other shrinks. By turning your antenna toward the larger pip, elevating it in this case, you again balance the pips and get back on target in elevation. To sum up this business on lobes, take a look at this miniature of a pip-matching radar. It has two horizontal lobes, like this, for measuring azimuth, and two vertical lobes for measuring elevation. Together, the four lobes make it possible for the radar beam to be centered on the target all the time, thus assuring you of highly accurate data. And of course, for each pair of lobes, there is a separate scope picture, one for measuring azimuth, one for measuring elevation. This type of pip-matching presentation is called the K-scope. So much for measuring azimuth and elevation. You'll remember that to measure range, you need only a single pip, A-scope, and the distance from the pip to the main bang represents the range of the target. As the target approaches your set, its pip approaches the main bang. The baseline, or sweep, as we've said before, represents the full range of your set. When we pick up a target somewhere within that range, it's obvious that the longer the baseline we have to represent the range, the easier it will be to read our target's position accurately, right down to the last yard. However, using a horizontal baseline, this is as long as it can be and still remain on the scope. But what we can do is stretch it out 3 times that length and put it around the edge of the scope. With this longer baseline, representing the same range that the short one did, we can read range a lot more accurately. Here's a typical circular baseline range scope, the J-scope used on the SCR 584. Now that we know why such a scope picture is desirable, let's go back to the electrostatic tube and see how we can get a circular baseline using the horizontal and vertical deflecting plates. Here's a front view of the plates. The electron beam is dead center since neither of the deflecting plates has voltage applied to it. Let's apply some and see what happens. We'll start with the deflecting plates that move the beam up and down. The sine wave represents the variation of the voltage we're going to apply with respect to time. Let's take it step by step. As the voltage climbs to this point, which we'll call A, the beam is deflected a corresponding amount toward the positive plate, upward in this case, to this point, which we'll also call A. When the voltage reaches B, its peak, the electron beam also reaches its peak on the scope, marked by B. When the voltage drops back to 0, marked by C, the beam returns to C, the center point from which it started. The same thing happens in the opposite direction. When the voltage reaches its downward peak, the beam goes down as far as it can. When the voltage returns to 0, the beam returns to center. That's one cycle of vertical deflection. Now let's look at the deflecting plates that move the beam horizontally. The same thing goes here. When the voltage reaches A, the beam moves horizontally to A. Every change in voltage produces a corresponding horizontal deflection of the beam toward or away from center. Next, let's see what happens when sine wave voltage is applied to both sets of deflecting plates. Remember that when we apply voltage to one set of deflecting plates, the electron beam is deflected upward. And if we apply the same amount of voltage to the other set of plates, the beam is deflected sideways. The combined action on both sets of plates is to move the beam along this diagonal path. To simplify the diagram, let's call the voltage applied to the vertical deflecting plates Y, and we'll label the vertical deflecting plates Y. We'll call the voltage on the horizontal plates X, and label its plates X. Now, since these voltages are going to be applied simultaneously, we can watch them more easily if we put one below the other. And to compare the movement of the voltages at any one instant, we'll put a grid over them. Let's see what happens when voltages X and Y both reach their positive peaks together. The beam is deflected to its extreme diagonal position. That's because the vertical plates are deflecting it all the way up, and the horizontal plates all the way to the side. As the two voltages complete their cycle of variation together, the beam follows a diagonal path, upwards to the left and downwards to the right. When the voltages vary together, like this, we say they are in phase. Now, let's have everything that happens to the X voltage happen half a cycle earlier than it happens to the Y voltage. When we have this half cycle lead, we say that the voltages are 180 degrees out of phase. Let's see what will happen to the electron beam under these circumstances. When voltage Y reaches its positive peak, the beam is still deflected to its maximum upward position. However, voltage X has reached its peak in the opposite direction, causing the beam to be deflected to the right. The result is again a diagonal path, but this time from upper right to lower left. Suppose that the phase shift was only half as much, 90 degrees instead of 180 degrees. Notice now that at the starting point of the cycle, the beam is already at its maximum left position. That's because voltage X is already at its peak, while voltage Y is at zero. A quarter of a cycle later, voltage Y reaches its peak and voltage X is at zero. The beam has moved through a circular path to its maximum upward deflection. As the cycle continues, the beam continues on its curved path, forming a circle. And of course, as the action picks up to its normal operating speed, you get the illusion of a circular baseline. Remember that this circle is the end view of a stream of electrons. If we vary the phase shift, the result will be some compromise between a circle and a diagonal line, an ellipse. But phasing isn't the only thing that will affect the shape of our circle. You can have the voltages 90 degrees out of phase and still not get a circle if the amplitudes are allowed to vary. If, for example, the amplitude of voltage X becomes less than voltage Y, it will change the circle into an ellipse, pushed in on both sides, because the horizontal deflection is not as great as the vertical deflection. However, once you've corrected the amplitude, you'll again have a perfect circle. If voltage Y is smaller, you'll again get an ellipse, but one which is squashed horizontally, because the beam is not deflected to its maximum vertical position. If both voltages decrease in amplitude the same amount, the result would again be a circle, but a smaller one. When the voltage amplitudes are corrected, the circle returns to its original size. So any change in the shape or size of your circle means an improper phase or amplitude adjustment. When you've corrected the amplitude and phase, you'll end up with a perfect circle of the right size. Now you've seen how the deflecting plates can form a circular baseline. When this pattern is projected onto the face of your scope, you get a baseline almost 3 times as long as the horizontal one we started with. Now that we have our circular baseline, how are we going to produce pips on it? Both sets of deflecting plates, remember, are busy forming the baseline, so something new must be added. It's a thin metallic rod inserted in the tube from the base through the center of the screen. This is the deflecting rod that will take care of forming the target pips. Here's how it works. Let's take a look at it from the front. We'll slow the beam way down so we can explain what goes on. There. That white dot is the end of the electron beam as it strikes the face of the scope. When negative voltage is applied to the deflecting rod, the electron beam, also negative, will be repelled from the center. If we leave the negative charge on like this, the beam keeps being repelled all the way around, and as a result, we get a bigger circle. If we remove the negative charge, the beam returns to its original path. If negative voltage is applied to the deflecting rod for only an instant, the beam is repelled from the center for only an instant, and then comes back to normal. The timer synchronizes the deflecting voltages so that every time the electron beam is at top center, the transmitter is triggered. The spillover energy, picked up by the receiver and applied to the deflecting rod, causes a pip to be formed. The main bang up at top center. This is 0 range. The returning target echo voltage is also applied to the deflecting rod, and another smaller pip will be formed somewhere on the circumference of the circle. As you can see, this scope gives us everything an A-scope did. A main bang, a target pip, and a baseline along which you measure range. But because our new baseline is circular, we can make it almost 3 times as long without increasing the size of the tube, thereby giving us a more precise means of measuring range. Since our baseline is circular, to measure range, we simply put a circular range scale around the edge, with 0 at top center. By reading range clockwise to the pip, you can tell at a glance how far away the target is. Here's that same J-scope you saw earlier. It's the coarse range scope of the SCR 584 and measures ranges out to 32,000 yards. To measure range even more accurately, crank this hairline around until it's on the target pip. That makes the echo appear as an expanded pip on the fine range scope, there at the right. It's also a J-scope and shows you an enlarged 2,000-yard segment of the set's entire range. With these 2 scopes, you can locate a target to within a few yards. So much for the J-scope. There was still a need for another type of scope, but before we get into that, let's take a short break. So far, you've seen how the A, K, and J scopes work. But remember, we said there was still need for another type of scope. For instance, here's a newly established beachhead on a Pacific island. Because of its advanced position, enemy bombers can attack the island from any point on the compass. Radar coverage is being handled by this SCR 545. Here it is, searching through a full 360 degrees. And there's a target. See it there on the search scope at the right. To find the target's range, you have to stop the antenna and bring it back onto the target. Then crank the pip into the notch on the range scope. To get the azimuth, the pip must be split and balanced on the azimuth scope. Only after you've made these adjustments can you report the range and azimuth of the target. But while you're doing all this with every target you pick up, what about planes in other sectors? As long as the set is looking in one direction, it's blind to everything else around it. So you can see that there was need for a new type of scope, a more versatile one. A scope that would measure both range and azimuth at the same time. One that would enable you to view the whole area at once and thus follow several targets simultaneously. Out of this need came the PPI, plan position indicator. With this scope, no matter how many planes there are in the sky around you, or from what direction they approach, your beam is continually searching and will pick up each one of them. The PPI paints a map for you of the surrounding area. Each target appears as a glowing blob of light at a point on your scope corresponding to its position in the sky. Each time the antenna beam passes over the target, the baseline, which is synchronized with the antenna, repaints the target blips on your scope. Thus, you can watch the movement of any number of targets at the same time without trouble or delay. Here's a sample of a PPI scope. And to show you how accurate a picture it presents of the surrounding area, here's the actual map. In developing this PPI scope, a new type of cathode ray tube had to be worked out. In order to project both range and azimuth at the same time, the deflecting plates inside the tube were replaced by a pair of coils around the neck of the tube on the outside. This is the other type of tube we mentioned earlier, the electromagnetic cathode ray tube. Let's look at the tube and coils from the front. When current is sent through the coils, it sets up a magnetic field between them. That deflects the electron beam away from center. As more current flows through the coils, the magnetic field between them gets stronger, and the farther off center the beam is deflected. As the current decreases, the electron beam returns to its normal center position. The deflection of the beam from center is always proportional to the amount of current flowing through the coils. And of course, just as on the A-scope, the deflection of the beam is synchronized with each transmitted pulse. When you apply current in the form of sawtooth voltage, you get the familiar trace and snapback movement of the electron beam. When it is speeded up, there's your PPI baseline, composed, as it was on the A-scope, of an electron beam sweeping back and forth so rapidly it creates the illusion of a solid line. When a target signal reaches the indicator circuits, it causes a greater number of electrons to be fired through the tube. The increased flow lasts for only an instant. Then the stream returns to normal, but the result on the scope is an intense glow of light at that point on the baseline, which represents the range of the target. Since each time the antenna is pointing at the target, there are several thousand pulses sent out and several thousand echoes return, the increase in electron flow at that point happens so fast that it forms a steady glow of light on the baseline at the range of the target. Range is measured out from the center of the scope, just as though a range scale were placed beneath the baseline. That blob of light in the center is the same as the main bang on an A-scope. The second blip is the target signal, and range is the distance between them. By the way, the process that makes the signals appear as blobs of light instead of pips is called intensity modulation. Okay, you know how the target signal is formed and how to measure range on this PPI. But how about azimuth? Well, those coils that cause the electron beam to sweep back and forth to form the baseline are designed to rotate freely around the neck of the tube. Since it was the current flowing through the coils that produced the baseline, when the coils rotate, the baseline sweeps around the scope. The rotation of the coils, and hence the sweep of the baseline, is synchronized with the antenna, so that the baseline is always pointing in the same direction as the antenna. So, by calibrating the edge of the scope, you can read the azimuth of the target at a glance. For instance, if a target shows up here, it's no trick at all to report its azimuth as 40 degrees. Notice, too, that since the glow of the target signal persists for some time after the baseline has painted it, you can make very accurate reports. For ease in operation, some sets have range markers as an integral part of the scope presentation, like this PPI on the AN-NPG-1. Some sets, like this AN-CPS-1, a microwave early warning radar, employ both range and azimuth markers on the PPI presentation, like this. If you want to examine a particular sector closer, it's possible to expand the picture by moving the sweep off-center in any direction. Now one quadrant is blown up to fill the whole scope. This presentation is called the EPI, or Expanded Position Indicator. On other sets like this searchlight radar, the AN-TPL-1, a pattern of geographical grids is placed over the PPI scope so you can locate the target in terms of grid coordinates. Another method of PPI operation employs two sets of deflecting coils which do not rotate as the antenna turns. Instead, the flow of current through the coils is regulated so that the resulting electromagnetic force causes the baseline to rotate. For instance, if current flows through these two coils with this polarity, the electron beam or baseline is deflected to one side, so. But if the polarity on the coils is reversed, the baseline is deflected to the other side, like this. Same thing is true of the other set of coils. Current flowing through them one way will deflect the baseline upwards. And a change in polarity will deflect the beam downwards. By synchronizing the flow of current through these coils with the antenna, the baseline will always point in the same direction as the antenna. Thus, by altering the flow of current through the four coils, like this, we can rotate the baseline without rotating the coils, which means we can forget about movable parts, bearings, and the added weight that goes with them. The lightness of this type of PPI makes it very useful for airborne sets. Echoes picked up on an airborne set enable the PPI to project a bird's eye view of the ground. The scope will indicate shorelines, rivers, railroads, ships in a harbor, buoys, even the projecting periscopes of a submerged sub. So the PPI is unusually valuable on bombing missions. In fact, all of the overcast and night bombing raids on both Germany and Japan were made possible by radar. But what about the night fighters that protect the bombers, or that go out to clear the sky of enemy bombers or night raiders? A night fighter pilot is after enemy planes rather than ground targets, and since long-range radar is pretty bulky, a radar-equipped night fighter usually operates with an early warning ground set. This MEW usually operates as a GCI set, ground control interception, and often uses this AN-CPS-4, known as Beavertail or Big Abner, to supply accurate height data. When a new target is picked up, challenged, and doesn't identify itself as friendly, the ground station vectors the night fighter to it. The controller watches the blip of the night fighter, guides him toward the target signal by radio. When the controller sees that the night fighter is close enough to the enemy plane so that its own shorter range, highly accurate radar can take over, he tips off the pilot. Now, having been guided to the approximate position of the bomber, the radar operator in the night fighter can pick him up and trail him with his AI, aircraft interception set. There's the target now. Let's see how these airborne radars work. Here's a diagram of our night fighter on the tail of an enemy bomber. The antenna revolves in a complete circle, but since the night fighter pilot is primarily interested in what's in front of him, only that area is presented on the scope. The rest is blanked out. This area, scanned by the beam, and of course any targets within that area, appear on the indicator or scope screen of the night fighter. A bomber that's ahead and to the right of the night fighter will appear up and to the right on the scope. Since this B-scope is intensity modulated, like the PPI you saw a while ago, the target appears as a glowing blob of light. However, the scope presentation isn't fan-shaped like the sector the beam scans, or like it would appear on the circular PPI. If it were, the short-range echoes would crowd together and be hard to spot. So, for ease of operation, electrical circuits actually stretch the picture into a rectangle. This is the presentation furnished by the airborne B-scope. When you turn on your AI set, this is what you'll see on the B-scope. It measures range vertically from bottom to top and azimuth horizontally. Now that we've seen the presentation, let's see how the B-scope produces this picture. Remember, with an electromagnetic tube, it's current flowing through the set of coils on the side that bend the electron beam up and down. When sawtooth voltage is sent through these side coils, we get the familiar up and snap back movement, thus forming our baseline. The baseline is synchronized with the transmitted pulse, like this. When the transmitter is triggered, the electron beam starts up toward the top of the scope as the pulse goes out. When the beam reaches the top of the tube, the set's maximum range, it snaps back and starts up again with the next transmitted pulse. Since the B-scope has a persistent screen like the PPI, the repeated spillovers form a constant glow at zero range, giving you the familiar main bang. Because the pulse is transmitted hundreds of times every second, the moving electron beam whips up and down so fast that it forms the baseline. Now, when a target is caught in this beam, the returning echo from it will form a blob of light somewhere along the baseline. Zero range is at the bottom of the scope, so if the target moves faster than your night fighter, the range between the two planes increases and the target blip will climb up the baseline toward the top of the scope, maximum range. So that you can spot the range of a target more easily, we can divide the fan-shaped sector which our antenna will sweep with imaginary range markers. For example, every mile, 1 to 5. Then we'll calibrate the face of the tube in the same way, with the 5 grid lines on the scope representing the mile distances in the sky. Here, the target is almost 5 miles away, so its echo appears just below the 5th range marker on the scope. So much for range. For azimuth, we'll add a vertical grid with the 0 marker in the center. Then planes to the left will appear to the left of center on the scope. Those to the right will appear to the right. This target is dead ahead, so it appears on the scope at 0 azimuth. But don't forget, the beam isn't stationary as we've been showing it here. It keeps sweeping through that sector, much faster than this, of course. And since the baseline is synced up with the antenna, each time the beam passes over the target, the baseline repaints the echo on the scope. Here's another target to the left at about 3.5 miles, and there's its echo on the scope. There's another to the right, this time at almost 2 miles. Because of the persistency of the tube, the glow from each target on the screen will be visible until the baseline repaints it on the next sweep. Now let's see how the tube does all this. You've already seen how current flowing through the 2 side coils produced the baseline. Varying the current flowing through the top and bottom coils makes the baseline sweep across the face of the scope. The flow of current through these 2 coils is electrically synced with the antenna, so that the baseline always indicates the direction the antenna is pointing. Of course, since the antenna revolves at 360 RPM, the baseline on the actual scope sweeps across so fast that you can't see it, but it enables you to see the target blip that much better, because it repaints the blip so much oftener. As you can see, the B-scope is excellent for helping you find the target and determining his range and azimuth. But in order to line up your guns on him, you must know his elevation. To get that, turn on your range marker and run it up to intersect the target blip. That gates in the C-scope, there at the left. It furnishes you both elevation and azimuth. Here's how it works. To feed data to the C-scope, the antenna, as it revolves, also nods, that is, elevates and depresses slightly. If the beam could trace its movement in the sky, the effect would look like this, painting a series of paths with each stroke a little lower than the preceding one. This is, in effect, what the stream of electrons does on the face of the scope. When the area has been covered from top to bottom, The antenna slowly elevates and the beam repaints the area from bottom to top. By moving up and down this way between the elevation limits of the set, the beam effectively scans all the space within this pyramid-shaped area in front of the night fighter. Any target flying into this area will show up in the C-scope. Let's say our target is right here. When the beam points in this particular direction, it hits the target and echoes are reflected back. Although the antenna revolves at high speed, it moves up and down comparatively slowly, and since there are thousands of transmitted pulses per second, a good many echoes will be returned while the beam is on the target. These returning echoes will brighten a spot on the scope screen at a point that corresponds exactly to the target's position in front of the night fighter. The face of the scope is marked off with a vertical azimuth line and a horizontal elevation line. The point where they intersect is dead ahead of you. Any blips that appear above the horizontal line are from targets higher than you are. Those blips that appear below are from targets lower than you are. So the C-scope is able to give you a scaled down picture of what you would be able to see with your own eyes if conditions permitted. For example, this enemy plane, which is to the left and below your night fighter, will show up on your C-scope as a blip to the left and below the intersection of your reference lines. To get on target in elevation, you simply maneuver your plane so the blip will come to the intersection. In this case, by turning left and diving slightly, you'll line up on your target. The addition of this clock-type mask enables the radar operator to guide the pilot in clock terms. When the blip is on the crosshairs, you know that you're on target in elevation and azimuth. Keep your eye on the B-scope, and when the blip gets within gun range, open up on him. In these three pictures, you've seen how radar works in principle and have seen many of its wartime applications. The same principles apply, of course, to radar reconverted into peacetime uses. Harbor control, navigation through fog and darkness by ships on the sea and in the air, blind aircraft landings, weather forecasting, meteorology in which radar locates and traces approaching storms, and a whole new field, astronomy, opened up when we made radar contact with the moon. On this sketch of the scope picture, you can see the main bang, and 238,000 miles along the baseline, the echo bounced back from the moon. Here's the actual scope receiving the moon echo. With a souped-up transmitter and hypersensitive receiver, the echo from the moon appeared as a good-sized pip, 238,000 miles away.